Even though we're in the session for design optimization, I will go 2 stages further and in how building information modeling can be used throughout design, operation, and design, construction, and operation. So many of you might not have heard of us. There's a lot of famous firms in the conference. We are a relatively young firm in the construction industry. We founded only in 2005, so that's most firms are in the 1950s, 1960s. But our firm is focused on the design, installation, and operation of structural health monitoring systems. And we design through building information modeling, and the whole process of building information modeling is used throughout this process. So I'll tell you more about that. We do all the international markets and activities are going through Australia, but like Roland introduced our project, the project that's going throughout this presentation is in Russia. And the reason for that is that in Russia it's a regulation to have structural health monitoring systems. So that's where most of the development in this area is. If you deal with structural health monitoring systems, there's a lot of data and software involved. We have our 100% owned company Element, which deals with the IT solutions in this field. So all the software development and even the business automation in BIM we do in that company. So I will go over what the company actually does. I mean, the main business is structural monitoring, but we do also follow the regulations for building equipment monitoring, such as the SCADA system, pump systems. Because we know our BIM systems, we do the MEP, communication and security system design. We do anti-terrorism analysis because our systems link to the regulations, and it's required to have real-time information. We should be able to detect explosions in buildings and immediately alert emergency response systems of the city. So our systems are integrated directly into Moscow city and the other Russian cities for the emergency response. Internationally, that is not a requirement, but if it's necessary, we have the capability and the software engineers to integrate this. So that's why we're called SODIS Lab. There's a laboratory aspect to this. A lot of research goes into these systems. As for the projects that we have been working with, I've listed only a few high-profile projects. All the Sochi 2014 Olympic stadiums have structural monitoring systems designed by SODIS Lab. We did all the building information modeling for these stadiums as well, and if we have won the Autodesk Innovation Award in doing so. Moscow City, where Roland talked about, almost all of the skyscrapers also have our systems. We also do our building information modeling there. Roland did his own BIM, so we didn't need to help Roland in that case. The FIFA 2018 is going to be held in Russia. We are working with building information modeling there, structural monitoring systems then and many more. More than 200 projects in total, and mainly in Russia just because of the regulations there. So my presentation will be in general about the procedure, how you get building information modeling from the standard procedure where you have first design. After your design, you do your construction, and then after your construction, you start your operation. The actual goal of building information modeling is to integrate all of this and, in a sense, get your construction done earlier. But that requires the integration of all these, all the steps at the same time. So, as an example, I give structural health monitoring and how we can reach this goal. I mean, building information modeling can be used in facility management as well, and that's where you need to use all those steps as well. But I will use structural health monitoring as an example. This graph you see here is actual data from one of the Olympic stadiums. This is a response of an earthquake that we measured. However, as you will notice later throughout the presentation, we don't really, and maybe you have seen our exhibition, the software does not really show this data directly. because the software is used for operation, but the data is there and the analysis is there as well. So the standard, the traditional view of building information modeling is that building information modeling assists in the design of a building. Everybody knows the clash detection that you can use in building information modeling when you use the structural system integrated with architectural system and integrated with MEP systems. That's in some sense what you see in this slide. You have the MEP systems on the right, the structural systems on the left. The drawings that can flow out of the structural out of BIM, and even that is that already can give you a large benefit compared to your traditional design. But the actual goal of building information modeling, I'm not sure if you've seen this kind of graph, but you can. Oh, this is not a laser pointer. Never mind. You can start the building information modeling is in some sense a circular process. If you start on the left side where you do the project programming, the project planning, that's where you start getting into the process of building information modeling already. You plan for the conceptual design. The architects can design in building information modeling, and at the same time you can employ structural engineers to start with the structural design. That continues into the detailed design and start to implement MEP design into the same system as well, and everybody works together. The analysis of the structure, the analysis of the MEP system, all this clash detection, you can get your documentation out of it, the design documentation, installation documentation, and it helps in the prefabrication or the fabrication on site. I think we've seen some presentations before how about the Leadenhall building. I'm not sure if you were in the previous session here. The prefabrication is very important to have a digital model, and building information modeling helps exactly with that. Leadenhall, take a look at the Leadenhall building in London. It's a very good example of what building information modeling can do. This flows into the construction, of course, and the logistics, what the Leadenhall building is a good example for. And then the actual goal is to go also in the operation and maintenance and the renovation. And that is often not used at this point. It's, you know the different levels of BIM. That's more like the last level, level 3 of building information modeling. That's where we are heading. So going to structural health monitoring, many people have the misconception that structural health monitoring is simply putting sensors in the building and to get some data out of it. Yes, it happens. It's necessary because otherwise you cannot know what is happening to your building. And these graphs show some of the frequencies of the building. But not everybody, especially the operators and owner, don't know what these measures are. You have to be a structural engineer to understand it. You have to have all the time series. You have to do the data analysis. You have to have the analysis people, big data. So the actual goal of structural monitoring is another circular diagram, just like building information modeling is, and that's why they fit so well together. Again, from the start, on the left side, you have your structural design of the building. You identify the elements of interest that you are worried about, you want to know about what the structure is doing. Sensors, you still deal with your sensors, so you have point information. You cannot have sensors everywhere. Then you install those sensors and you have a communication system to get this data from the building. You install this and then you have to analyze what is happening to the building. This analysis, that is where we come in with the branch to real-time safety. The software that we work is an operational software that keeps track of the real-time safety. But the analysis also can use for validation of structural engineers. So how the building is reacting compared to your initial design. You know that the Burj Khalifa has this system, the Shanghai Tower has a system. We heard a presentation of the Ping An Tower about their structural monitoring system. Almost all top buildings will have these systems because it will the evaluation of this data will give you improved future buildings. But it gives you also this real-time safeties. And therefore, you go back to the improved design process. You get better buildings. It's in a sense the circle of performance-based design. But I know that performance-based design is mainly used on, they base it on extensive simulations. But The actual improvement can only happen on valuable data. And we know some people, some companies have saved millions in construction costs just because they have so many projects. They can improve their design and save a lot of materials in future processes, future construction projects. One in quote I would like to address is from the United States Geological Survey. You might think the USGS just does earthquake monitoring. They are famous for that. You get sometimes your earthquake warnings from all over the world. That comes from them. But they actually do structural monitoring as well. And they do this since the 1970s. Not many people know this. But when I went to the United States Geological Survey, they actually told me that if it were not for the monitoring that they do this analysis, it feeds back to the building standards, we would still not have the same kind of heavy and, low rises as the Empire State Building. The fancy buildings we see today, they would not be possible if it were for structural monitoring. So it is correct that the CTBUH has identified structural monitoring as one of the main important research factors for the improvement of buildings. And if you look at the safety of buildings, this is a slide that nobody really wants to see. But I don't know if you're all familiar with these events. On the left side, you have the collapse of the I-35W bridge in Mississippi, the Mississippi River, I think, in Minnesota. That bridge was standing there for 40 years, and then the result of the collapse was a design fault. If you design something and it still stands for 40 years, is it really a design fault? You can monitor this and you can keep track of what is happening to the bridge and see the trend that that there are weakening elements and a collapse could have been prevented if they were instrumented. And that's why the new bridge is now the most instrumented bridge in the United States. The two buildings on the right are in a sense not structural, well, they are structural failures, but in a sense owners who don't follow their regulations. That is in some sense why regulations might be assisting to follow the owners and check the owners why that buildings are being constructed according to the standards and not trying to save costs at every corner, and so that you have the worst structural failures in the world. Because the top one, more than 1,200 people died. The bottom, I think about 500 people, just because the owners didn't take care of their occupants. And on the left side, unfortunately, that's a Shanghai tower. They started to dig a hole on the left side and put all the sand on the right side, and the building slowly started to tilt. It's a very easy example of how a single sensor in this building would be able to see that the tilt is happening, and it could send it out an alarm, and it could have stopped. And this is, of course, $1 million of loss in the building alone. There was a lawsuit as well. This person is now in jail. It could all have been prevented. So how at the backbone of a structural monitoring system are, of course, the sensors. And it's not just only an acceleration sensor that measures the vibration. It's the whole range of all geotechnical sensors embedded in the concrete, welded to steel, installed on acceleration, strain gauges, environmental monitoring to keep track of your seismic performance, the wind performance. And it's not only temporary, it's like you can do it permanent, lifetime monitoring, but also during construction. And a lot of the construction companies are using monitoring nowadays to keep track of the correct building process, that the building is going up straight and not going to tilt it one way. The Burj Khalifa is a perfect example of how they used GPS in keeping the core upright. The total stations, the traditional survey was impossible because the building was so high. They needed to have the GPS system to keep the formwork, the core going up straight. So the process of, like I mentioned, it's not just the sensors. The process of designing or creating a structural monitoring system involves quite a lot of elements. In the design phase, for example, of the monitoring system, also in the design phase of a building, you have to identify your structural threats, such as seismic, wind, or actually the explosions I mentioned earlier. You have to analyze the buildings to know where the weak points are and where the best location is for your sensors, like the critical structural elements that need to be monitored for safety. Based on those elements, you can choose your parameters, and parameters are, in this sense, if you want to know the strain, the acceleration, but also the movement, like displacement. If you have, we heard some presentation about seismic isolation, then you want to know what is happening to the bearings, for example. You want to measure between the building and below and see how the bearings work, something like that. And the safety criteria are based on this modeling, but also on the building standards, that you don't exceed the limits as set by the standard for safety. Then in the construction phase, you start to actually install these sensors. But then you have to install your communication system to get all the data out. You have to have a server to log all the data, store it, do all the analysis. Because in the operation area, you see the operational software and the data analysis, we actually you have to link all the data to a mathematical model of the building. When you design the building, you do your simulations and your finite element analysis. But when you want to use this system for the operation, you need to know what the actual building is doing. So there's always a certain degree of error in your simulations compared to the actual measurements. So you need to, in the construction phase, you measure for a certain period, and then you update the mathematical model so that you know that your mathematical model matches with what you actually have measured. And during the operation, you analyze the data. There's a possibility for research collaborations. Universities can do the research institutions, just to get this circle ready for future improvements. So in our company, it's not just one software, of course. It's for in the design phase, we use our building information modeling tool. Autodesk Revit is the main software in that case. But mathematical modeling cannot be done in it can be done in robot, but we prefer ANSYS as well because it's much more detailed in what information we can get out of it. And in the management of the systems is we have our own program, Lemon Pro, which is a business automation system or a business management system, but also Autodesk 360 we use in that. But in the operation, we have our own developed software. And if you have been to our exhibition stand, you can actually see this real-time software in operation. The building model, which is standing there, is not an actual building. It's just a model that shows how the sensors integrate to the system. So if you were to shake this building, as if it were an earthquake, it immediately detects in the software that there's an earthquake. So an operator in the building can see directly what is happening with the building. So just some overview of how we use all these different systems. On the left side, you see this is in some sense our project management work. On the left side, you see our task system. I mean, we deal with a lot of projects. We have our time planning online. Most and all of it is done in the cloud. So that's where Autodesk 360 comes in. We develop our building information modeling. We have in this system we integrate the Autodesk models into the cloud online. So anybody in the company has the direct link between a discussion system and Autodesk and can discuss with the developers in what we are doing and what needs improvement. Additionally, this is more in the development of the models that we use. In building information modeling, we have developed several tools for sped up 3D modeling. For example, on the left side, you have the left top. Sorry, you have a 2D to 3D automation system. This one was used for the bobsled track in the Sochi Olympic Games. you have the coordinates of all the locations and the shape of the system and the shape of the project, and it will create a 3D model automatically. Then we go to the operational stage of how building information modeling can be used in there. You can use it in the way of facility management. The structural monitoring system is a decision support system for monitoring, but building information modeling is just more than only. I'm talking in general about the building information modeling here, not only the structural health monitoring. You can use building information modeling as facility management, keeping track of everything that's in your building, certifications in this case. We use it for our sensors. Sorry, I need to. Then we have a special tool that does our survey of the building, the structural system on the left side, the left bottom. You can see that we investigate all the structural floors, select all the critical elements, link them to the sensor system, link them to the data. That is then used in our operational software, where this software, like you have maybe seen in the exhibition, is in some sense the Microsoft Word for structural monitoring system. It has a Google Earth-like interface for browsing through your 3D system. It has and on the bottom side you can see the warning systems, all the sensors that are present. Clicking on the sensors and you can get to the raw data as well. So there's the possibility for doing your own analysis. Sorry, I got a very dry mouth. So to conclude, if you were to follow the latest International Building Code from 2012, there actually is an appendix in it that says that if the first, second, what was it in exactly? At least S1, the first, second seismic acceleration, if that exceeds 0.4 G, then a structural monitoring system is required. And that's why you see in Los Angeles or in California, the United States Geological Survey is monitoring all the buildings that are being constructed there. But if you extrapolate this to the world, all the red areas are the areas that are seismically active and, in a sense, require monitoring according to the standard. But everybody knows the IBC is only law until the government of that country says so. So it's one way of maybe CTBUH can assist in getting everybody to know which standards to follow where and get the improvement of the systems. Thank you.